Electrochemistry Part 2, Galvanic cells. Now, galvanic cells or voltaic cells, the names are interchangeable, are cells which occur with spontaneous reactions. And these spontaneous reactions will actually produce current, where our electrolytic cells that we looked at consume current. In a galvanic cell, each of the half reactions is separated, while in an electrolytic cell, they were kept together in one pot, so to speak. Now, the galvanic cell half cells are connected externally, and these two half cells kept separately connected by some wire to each other. This is the kind of thing that occurs in a battery. A battery contains half cells, and the half cells are connected by a wire. If you think of the positive end and negative end of, say, a 9-volt battery, you have two different connections which go to it to make sure that the circuit is complete. Now, in a galvanic cell, the oxidation half cell and the reduction half cell usually have electrodes which are in the solution. So, for example, a copper electrode would be used in a copper solution. The electrode is generally of the same species as what is being reacted in the oxidation reduction process. The half cells are connected to each other with a wire, and often they'll be connected to some sort of voltmeter or ammeter to measure the current which flows from the reaction. The half cells are also connected together by a salt bridge. And a salt bridge is usually a 5% agar solution, which contains some sort of ionic salt, like potassium chloride or potassium nitrate or some other salt. And what this does is allows us to maintain ionic stability in a process where we're consuming reactants. The salt bridge lets ions travel from one compartment to another and also serves to complete the circuit as they move the current through the salt bridge. So looking at the galvanic cell, there are three different functions to a salt bridge. One is that it allows electrical contact between the two solutions. The second is it prevents the solutions from mixing or short-circuiting. And the last is that it maintains electrical neutrality for each of the half cells because positive ions can flow into the half cell which is becoming more negative, and negative ions can flow into the half cell which is becoming more positive. In a standard cell, the reactants and products will occur at standard state, where standard state is 1 molar. So if we look at an example here, we have an example of a copper sulfate and silver nitrate solution. So on the anode, the oxidation process is copper being oxidized to copper 2+. At the cathode, the reduction process is silver being reduced to silver metal. The anode in this case is negative, and the cathode is positive, which is backwards from the electrolytic cell, where the anode was positive and the cathode is negative. This is because this is a spontaneous reaction, not a non-spontaneous reaction. So with a spontaneous reaction, the electrons flow from anode to cathode in the same way, but because they're being produced by the anode builds up negative charge. So looking at the solution here, we have a salt bridge in the middle. That salt bridge in this case contains potassium nitrate. And so as my oxidation process occurs in the left-hand cell, the anode, we're forming copper 2+. Copper 2+ is being released into solution off of the copper electrode, which is being consumed. As copper 2+ moves into solution, it starts to make the solution more positive. Nitrate ions can move from the salt bridge into solution in order to help to equilibrate the charge. We can also take some of those copper ions and put them into the salt bridge. In the right-hand cell, the reduction process, we see that silver from the solution is being plated onto the silver electrode. Silver plus is moving on to depositing solid silver on the electrode. As the silver moves from the solution to the electrode, we lose positive, which starts to build up negative charge with the counter ion. To balance this out, we have to add more positive charge into the solution, and that generally comes from something like potassium. Potassium moving into solution will form a rebalance of the positive that is being lost from the silver. We can also take some of the counter ions, like in this case silver nitrate. Some of that nitrate can move back into the salt bridge and help to equilibrate the ionic character between both sides. So looking at an example of a galvanic cell, we have a zinc copper cell. The Danel cell is what it's called, and a zinc copper cell consists of copper sulfate and zinc sulfate in solution. Initial voltage of a Danel cell is 1.10 volts. 1 volt is 1 watt per amp, or 1 kilogram meter squared per coulomb per second, or 1 joule per coulomb, or 1 kilogram meter squared per amp per second. These are different units for the volt, which will be more important later on. Now, in this sort of electrode, the mass of the zinc electrode decreases and the concentration of the zinc 2 plus increases. This is because zinc is being oxidized. The mass of the copper increases and the concentration of the copper 2 plus decreases. This is because the copper is being reduced. Zinc is oxidized to zinc 2 plus, copper is reduced to copper metal. So we have zinc plus 2 electrons, zinc producing 2 plus 2 electrons, copper plus 2 electrons producing copper solid. So a net reaction of copper plus zinc yielding copper 2 plus zinc yielding copper plus zinc 2 plus. The anode will release electrons and the cathode will consume the electrons. The electricity still moves from anode to cathode and is spontaneous in the galvanic cell. So as we said, then we have a flow from negative to positive in this case rather than from positive to negative like we do in electrolytic cells. So the salt bridge will maintain charge by releasing the salt into solution. So generally in something like this, the Danel cell, we would use potassium chloride as our salt bridge. We can move the zinc 2 plus into the salt bridge, and we can also move some of the sulfate into the salt bridge as we start to move potassium and chloride out of the salt bridge, and that helps to maintain the charge neutrality. So looking at the overall cell, it looks very similar to the copper and silver cell that we saw a minute ago, except now the copper is at the cathode and undergoing the reduction process, while the zinc is at the anode undergoing the oxidation process. So we have 1 molar solutions of each, because that's our standard cell. We have chloride moving into the zinc anode, because that will help to balance out the positive zinc being produced. We have potassium moving into the copper cathode to help balance out the copper being consumed. And we have a voltage of 1.1 volts. The reactants are consumed and the voltage will begin to drop. So as the reaction continues, voltage depends upon the presence of that particular solution's concentration. As concentration changes, voltage will change with it. If I had a cell that was 2 molar in concentration instead of 1 molar, the voltage would not be 1.1, it would be something different. The voltage itself is caused by an imbalance in the equilibrium. When the voltage reaches 0, that will be at the point which the cell will reach equilibrium. So when the process reaches equilibrium, we no longer have a potential to react on either side. And so because we lack that potential, the voltage drops to 0. Now this doesn't mean that the concentration of the solutions will be 0. It just means that they'll be at equilibrium at this point. We can represent the cells for a galvanic cell using vertical lines. We use one line between the electrode itself and its solution, and then 2 lines between the 2 half cells. So if we look at the Danel cell, we have the zinc electrode and the zinc 2 plus solution as a 1 molar concentration, then a double bar, and then we have the cathode, with the copper 2 plus as a 1 molar solution, and the copper electrode. The KCl is listed as a salt bridge, and that gives us a very simplified version of our process. If the electrodes were to exchange solution, if I put the zinc into the copper and the copper into the zinc, the copper would be inert, nothing would happen to it, but the zinc would react directly with the copper solution, and the cell would quote-unquote short circuit. There would be no flow of electricity because the reaction would be occurring directly at the electrode, where we're going to be consuming the zinc and producing the copper. And in this case, the energy would just be lost as heat, would not be produced as electrical energy. So when you have a short circuit, that's generally because you have a direct contact between your reacting half cells, and so you lose that conductivity that you normally would have because of the separation of the half cells. Looking at the copper-silver half cell that we started with, if we put a copper strip into 1 molar copper sulfate and a silver strip into 1 molar silver nitrate, we would find that the voltage would initially be 0.462 volts. The mass of the copper would decrease, and the mass of the silver would increase. We can look at an activity series to help us understand why a galvanic cell happens the way that it does. Think of a galvanic cell basically as being a separated redox displacement reaction. So looking at the activity series, zinc is above copper in the activity series. So when we had the Danel cell with the copper and the zinc was being oxidized and copper was being reduced. Now here with the copper-silver cell, copper is above silver, and so copper is being oxidized and silver is reduced. So now copper serves as the anode, or the negative electrode, where the oxidation occurs, and silver serves as the cathode, the positive electrode, where the reduction occurs. Electron still flows from the anode to the cathode, and we're flowing negative to positive in our galvanic cell. So copper forms copper 2 plus with the production of 2 electrons. Silver takes in 1 electron to produce silver metal. So our net reaction is copper plus 2 silver ions produces copper 2 plus ion plus 2 silvers. Now, which of these is the cathode or the anode? As we said, depends upon the activity of the two metals. We can use galvanic cell experiments to actually form the basis of the activity series that we look at. So from our understanding of a series of galvanic cells placed against each other, we can predict the activities of different galvanic cells using the activity series that we have. So the establishment of the activity series came from galvanic cell experiments, and using the activity series, we can predict, putting two different types of half cells together, what the voltage will be based upon the standard potentials that are from those particular reactions, and which one is serving as an anode or a cathode in that particular pair.